Arithmetic and fractions, properties of real numbers. Let me begin by saying this video really starts at square one. It starts with the very basic properties of all of mathematics. And if you're reviewing math, this is a wonderful place to start. We'll cover everything from the basics. But if you're already familiar with math, if math is something you're reasonably good at, then you probably don't need to watch all these introductory videos. What I'd strongly suggest is just skip ahead to the summary, read the summary. If there's something in the summary that makes absolutely no sense, then go back to the video and watch the video. But don't force yourself to watch the video if it's stuff that's going to be way too easy for you. It's very important to know yourself and pace yourself in this process. For folks who really want to learn everything from the beginning onward, let's start at the beginning. When the test says number, it always means a real number. What's meant by a real number? Well, a real number is any number on the number line. This includes round numbers as well as fractions and decimals. So all the numbers pictured here as well as all the numbers and all the spaces in between. Numbers like 1/3 or pi or the square root of 7. All of these are numbers. They're all real numbers. When the test says number, this number could be any number on the number line. It could be positive, negative, or zero. It could be a whole number or a fraction or a decimal. This is one of the ways that the test loves to trap people. It loves to begin a math problem. X is a number, and then it goes on, and people assume that since X is a number, it can only be 1, 2, 3, 4, 5. In other words, that it has to be a counting number. People forget about negatives. They forget about fractions and decimals. Very important not to fall into that trap. If you see the word number, you have to be thinking about all these categories altogether. We will discuss fractions and decimals in later videos. Right now, notice that 0 is the only number that is neither positive nor negative. So we have these two very large categories, positive and negative. 0 is the only number on the number line that doesn't fall into either one of those categories. One special type of number is the integer. Integers include all positive and negative whole numbers. If the question asks about integers, it could be any number in this set. It could be the positives or the negatives. If the question asks about positive integers, then that's ordinary counting numbers, 1, 2, 3, 4, 5, 6, etc. Very important to keep these three sets straight. Sometimes questions will ask about numbers, sometimes they'll ask about integers, sometimes they'll ask about positive integers. Those are three different sets. It's very important not to confuse them. Back to all the real numbers. There are a few vocab words you need to know. These concern the four fundamental operations. You may want to pause the video here just to verify to yourself that you know these four terms. The result of addition is called a sum. The result of subtraction is called a difference. The result of multiplication is called a product. The result of division is called a quotient. These are four vocab words you need to know. There are also some fundamental arithmetic properties common to all real numbers. To discuss these, I will use A, B, and C to represent real numbers. These are terms you don't need to know. You don't need to know the names of the properties. All you need to know are the properties themselves. The first one is the commutative property, the ability to switch the order. So, for example, we can switch the order of addition. A plus B equals B plus A. Doesn't matter which order we do it in, we get the same answer. Similarly, with multiplication, we can swap the order around. A times B equals B times A. Again, we can swap the order around, we get the same answer. Addition and multiplication are commutative. Division and subtraction in general are not commutative. If we swap the order around to subtraction, we get different answers. 7 minus 4 does not equal 4 minus 7. But keep this in mind. If we rewrite the subtraction as the addition of a negative, that's a very sophisticated move, then it would be commutative. So 7 minus 4, we could express that as 7 plus negative 4, and then we could swap the order, negative 4 plus 7. So we could actually perform that swap if we needed. So all these are properties you need to know. You need to know what you can do with these numbers, but you don't need to remember the word commutative. That word will not be on the test. The second property is the associative property, the ability to group things. So if we're adding three numbers, we can group them. We could add B plus C first, or we could add A plus B first. Either way of grouping leads to the same answer. Here we can add the 3 and the 5 first, or we could add the 2 and the 3 first. Either way, we get the same answer. Similarly, with multiplication, we can group them B times C first or A times B first. If we multiply the 3 and the 5 first, or we multiply the 2 and the 3 first, either way we get the same answer. Addition and multiplication are associative. Subtraction and division in general are not associative. Again, you need to know what the numbers do. You don't need to know this word, associative. That's not a word that the test will test you on. The distributive property. This one is a big one. First of all, multiplication distributes over addition, and it distributes over subtraction. So we could do the addition or subtraction first and then multiply, or we could multiply times each piece and then perform the addition or subtraction. So for example, we can add 2 plus 3 first and then multiply, or we can do 6 times 2, 6 times 3 first, and then add those two products separately. Either way, we get the same answer. Similarly, with subtraction, we could subtract the 3 and the 7 first, get the 4, multiply that by 12, or we could multiply the 12 times 7 and separately multiply the 12 times 3 and then subtract those two products. Either way, we get the same answer. There are other properties that concern the special numbers 1 and 0. The first one is multiplying and dividing by 1. Very simple. We don't change a number when we multiply or divide by 1. So we can represent that symbolically this way. A times 1 equals A divided by 1 equals A. Absolutely no change if we multiply or divide by 1. Multiplying by 0, anything times 0 equals 0. Again, very simple. So A times 0 equals 0 times A equals 0. So we're perfectly allowed to multiply by 0, and we always get 0. We're not allowed to divide by 0. That's a very important point. The zero product property. If the product of two numbers is 0, one of the factors must be 0. So if A times B equals 0, then A equals 0 or B equals 0. And notice that the word or there, that's an essential piece of mathematical equipment right there. That's actually part of the math. That's not decoration. That creates the logical connection between the two equations. The zero product property is very important in factoring and in solving quadratics. So you'll run into it there. Those are in the algebra module videos. Dividing a number by itself. When any non-zero number is divided by itself, the quotient has to equal 1. We can express this as A over A, or A divided by A equals 1. Again, very straightforward. So in summary, the test is going to use the word number, and this always means any real number, not just positive integers. It's very important to keep numbers versus integers versus positive integers straight. Those are 3 different sets. Know those 4 terms, sum, difference, product, and quotient. Those are actual vocab words you need to know. And know the properties. Again, we don't need to know the names of the properties. We just need to know the properties themselves. Here we have the commutative property and the associative property. Here we have the distributive property, which is a really important one, and then all the properties concerning the special numbers 1 and 0. Arithmetic and fraction, positive and negative numbers. In this video, we will discuss how to add and subtract positive and negative numbers. Now, this is a very basic topic. Again, if you are proficient in this topic, do not feel compelled to watch this entire video. This is a video designed to get people comfortable with this topic if it is unfamiliar or they have some uncertainty with the topic. So wherever you are starting, I will assume that you are proficient with 2 basic cases, how to add 2 positive integers or how to subtract 2 positive integers when they're in the form bigger minus smaller. First thing I'll say is, if you need practice with this, practice every day. It's very important to be proficient in 2-digit addition and subtraction. Be able to do that as mental math. That will make the test much smoother. Now, the good news is, if you can do these 2 things, you can do anything else. This entire topic is very easy if you know these 2 things. There are many ways to discuss this material. Let's begin with subtraction. Some mathematicians would say subtraction doesn't really exist. What does that mean? Well, subtraction of any number can be rewritten as the addition of a number of the opposite sign. And so some mathematicians would say that this addition is actually the true form. So let's make sure we understand this. Subtraction of any number can be rewritten as the addition of a number of the opposite sign. Here are 4 different instances of subtraction. We have a positive minus a positive, a negative minus a positive minus a negative, and a negative minus a negative. In all 4 cases, we could rewrite that subtraction as addition of a number of the opposite sign. In the cases where we are subtracting a positive, that's the same as adding a negative. In the cases where we are subtracting a negative, that's the same as adding a positive. We'll notice that we get some simplifications, but it's not a simplification in every case. For example, in the first one, it looks like we were better off where we started. We were better off without changing it to addition. In the third one, it looks like we clearly made things better off by changing it to the addition of 2 positive numbers. In that fourth one, notice that now it's addition, it's commutative, so we can switch the order around, and when we switch the order around, we can rewrite it as subtraction, and that's much easier. So sometimes this is really an important move for simplification, but not always. You don't always have to rewrite subtraction as addition, but it can be a very good simplifying trick to have up your sleeve. Notice in particular, for the case positive minus negative, this trick will always simplify it. It will always become positive plus positive, which is one of those fundamental things that I assume you know how to do already. Now let's look at that tricky double negative case, which could appear in the form negative minus positive or in the form negative plus negative. The big idea is we can always factor out a negative sign. Now what does this mean exactly? Let's look at that first one, negative 46 minus 37. We can factor out a negative sign. If we factor out a negative sign, everything inside becomes positive. So it just becomes 46 plus 37, addition of 2 positive numbers. So you perform that addition and then just stick a negative in front of the sum. You might want to try these others on the page. Pause the video here, try these others, and then you can compare your answers to mine. Here are the answers. One other case folks find tricky is the case small positive minus big positive, which also shows up as small positive plus big negative. Here, the big idea is factoring out a negative sign reverses the order of subtraction. So what does this mean exactly? Suppose I have 23 minus 64. If I factor out a negative sign, then what I get is subtraction in the reverse order, 64 minus 23. Well, now that's bigger minus smaller. That we can do. That's one of the fundamental skills. So do that subtraction and then just stick a negative sign in front of it. Let's look at another one. 26 minus 63. Factor out the negative and we get a negative in front of the reversed order of subtraction, 63 minus 26. Perform the subtraction and stick a negative sign in front of it. Here are some more. You might want to pause the video here and practice these on your own. Here are the answers I get. Very important that you're able to do things like this, and it's very good practice for mental math to be able to do this in your head. These ideas allow you to change any addition or subtraction to either the sum of 2 positives or the difference of larger minus smaller. Here I just discussed integers for simplicity, but all these same ideas would also be true for positive and negative decimals and fractions. The core skills are addition of 2 positives or larger positive minus smaller positive. From here, if we're doing positive minus negative, we can change that to positive plus positive. If we have the double negative case, we can factor out a negative sign. And whenever we have smaller minus bigger, we can factor out a negative sign, reverse the order of subtraction, and then what's inside bigger minus smaller, that's something we can do. Mental math. In the previous lesson, I encouraged folks to practice mental math, adding and subtracting. In this video, I will suggest a couple of tricks that can make it easier to do calculations in your head. Remember, even though you get a calculator on the GRE, doing as much mental math as possible is an enormous time saver. People don't realize this. If you're reaching for the calculator in every single problem, that's going to take everything much longer on the math section, and you're going to run into time problems. It's going to be a time crunch at the end. It's much more efficient to use the calculator as little as possible and to rely on mental calculations as much as possible. In this video, I hope to encourage you that you can add or subtract any two-digit numbers in your head. Practice with this until you're confident with it will enormously strengthen your overall confidence with arithmetic. And again, let me say, these tricks I'm going to show, they may be unfamiliar. It's going to take time to practice them and get comfortable with them. But once you get comfortable with them, you can really master this stuff, and it will be enormously to your advantage. The first trick is simply to remember, of course, that every two-digit number can be written as the sum of a multiple of 10 and a single-digit number. So, for example, these numbers can be written this way: multiples of 10 plus single-digit numbers. This is just ordinary place value. There's nothing particularly sophisticated here. Okay, how is this helpful? Suppose you have to add 47 plus 36. Well, think about it this way. 47, of course, is 40 plus 7. 36 is 30 plus 6. We can separate out, we can add separately the multiples of 10 and the single digits. 40 plus 30 shouldn't be bad to do in your head, and 7 plus 6 should be easy. So we add those. Now we just have to add those two sums, put that all together. And of course 70 plus 13 is 83. That's the sum of the original two numbers. Now try a few of these on your own. You may find it helpful to pause the video as you try these. And these are the results here. We can use this same fact at least some of the time for subtraction as well. If each digit of the first number, the tens digit and the ones digit, is bigger than the corresponding digit in the second number, then we can separate by digits to simplify the subtraction. So for example, if we have 59 minus 31, we can think of each one of those as a sum, 10 digit plus 1 digit. We can group them, so we're subtracting the multiples of 10 and separately subtracting the ones digits. So 50 minus 30, of course, is 20. 9 minus 1 is 8. Putting those together, the result is 28. Here are some more subtraction problems of this genre. Pause the video and practice these in your head. And these are the results here. What about if the smaller of the two numbers, the one you subtract, has a bigger ones digit? So for example, 56 minus 19. The 9 is bigger than the 6. What do we do here? Well, for this one, we can't simply treat the digits separately. Grade school math teaches folks about, quote, borrowing a 1 from the tens column, but that's a pain for mental math. Instead of the borrowing thing, think about it this way. If we are subtracting any two numbers, we could add a new number to each of them, and the difference wouldn't change. So for example, a minus b. A minus b will equal a plus k minus b plus k. In other words, if we add the number k to both a and b, the difference stays the same. In essence, in doing this, we're adding both positive k and negative k. One of the k's is being added and one of the k's is being subtracted. And of course, k plus negative k is 0. Adding 0 doesn't change the difference. We will take advantage of this fact by adding just enough to the smaller number to move it up to a multiple of 10. So for example, 56 minus 19. Well, 19 is 1 less than 20, so I'm going to add 1 to it. Well, if I add 1 to that, I have to add 1 to the other. So 56 plus 1 is 57, 19 plus 1 is 20. Then when I do the subtraction, it's just subtraction in the tens digits. So 50 minus 20 is 30. The answer is 37. Another example, 71 minus 26. 26 is 4 less than 30, so I want to add 4 to that. If I add 4 to the first one, I have to add 4 for the second one also. I have to add 4 to both of them. So adding 4, 71 moves up to 75, 26 moves up to 30. Well, now again, we just have to do subtraction in the tens digit, and the answer is 45. Here are some more examples for practice. Pause the video here and practice doing these in your head. And here are the results here. In summary, practice mental math. This was the first video in which we're going to discuss mental math tricks. The more you can learn these mental math tricks and apply them and practice them, the more efficient you'll be on the quant section, and also just the more confidence you'll have with math overall. You can simplify mental math for the addition of two-digit numbers by treating the digits separately. You can also treat the digits separately in subtraction if the number subtracted has both the digits smaller. And we can also simplify subtraction by adding the same number to both terms. More on positive and negative numbers. And again, I'll give you the warning for these very basic videos. If you really know all this stuff inside out, you don't need to watch the video. In this video, we're just going to talk about multiplying and dividing positive and negative numbers, and we're going to talk a little about absolute value. So first of all, the rules for multiplication and division of positive and negative numbers are considerably simpler than the rules for addition and subtraction. First of all, let's talk about the sign rules. So for multiplication, positive times positive has to be positive. Negative times negative, the two negatives cancel, and we get a positive. But positive times negative gives us negative. So in other words, same sign gives us a positive product, different sign gives us a negative product. The rules for division are similar. Positive divided by positive is positive. Negative divided by negative is also positive. The negatives cancel. But if we do positive divided by negative or negative divided by positive, we get a negative. And so again, same signs lead to a positive quotient, different signs lead to a negative quotient. So we can just put everything together and combine sign rules. If we multiply or divide numbers with the same sign, the results are positive. If we multiply or divide numbers with different signs, the result is negative. So that's a really big fundamental idea there. It's important to be very clear on that. So when we're multiplying positive and negative numbers, really the easiest thing to do is first think through the sign rule. Do I want to end up with a positive answer or a negative answer? You should always know that before doing any calculations. Then usually the easiest thing to do is treat both things as positive, just perform the multiplication as if everything were positive, and then add the appropriate sign at the end. So for example, negative 6 times negative 7. Negative times negative, that's positive. So that's going to be the same as 6 times 7, and 6 times 7 is 42. So positive 42 is the answer. Negative 65 over 5, that's going to be negative. And of course, 65 divided by 5 goes into 65 13 times. And so this is just negative 13. In the last one, negative 30 minus negative 30 divided by negative 12. Well, negative divided by negative is going to be positive again. It's going to be the positive fraction, and then we can reduce that fraction to 5 halves. And we'll talk more about fractions in the next module. Another topic related to positive and negative signs is absolute value. Many folks need to update their understanding of this. The naive definition, kind of a middle school definition of absolute value, is it makes everything positive. And this is a little problematic because, yes, it is true that it keeps a positive number positive, it makes a negative number positive, but it's also true that the absolute value of 0 is 0. See, 0 is neither positive nor negative, so it doesn't make 0 positive, it leaves it as 0. And so that's actually an important distinction there. Here's a much better way to think about absolute value. Much more sophisticated definition, the absolute value of a number gives the distance of the number from the origin. In other words, gives the distance of that number from 0 on the number line. So first of all, this is totally consistent with our previous understanding. The point 6 is a distance of 6 from 0 on the number line. The point negative 14 is a distance of positive 14 from 0, because distance is always positive. And of course 0 is at a distance of 0 from 0. This new understanding has important implications in algebra, and so we'll just be talking about some of the very basics of algebra here for a moment. For example, the absolute value of x is the distance of x from the origin. And again, distance is always positive, so whether we're at positive 50 or negative 50, we're at a distance of 50 from the origin. What if we want the distance from x equals plus 5? Well, of course, the classic operation for finding distance on the number line is subtraction. So we're going to subtract and then take the absolute value of the difference, x minus 5, the absolute value of x minus 5. And of course, this works with numbers, if we think about it, because if we plug in 7, 7 is a distance of 2. Take the absolute value of 7 minus 5, that's absolute value of 2, which is 2. If we go down to x equals 3, that's also a distance of 2 from 5. We plug in x equals 3, we get 3 minus 5, absolute value of negative 2 is, of course, 2. And so in either case, it works. We're getting the distance from 5 on the number line. Now suppose we want the distance from x equals negative 3. Well, the same pattern, we're going to subtract the absolute value of x minus negative 3. But here's the tricky part. When we subtract a negative, we get a positive. And this is what really can confuse people. Why are we adding when it's a negative? Well, really what's happening is we're subtracting a negative, and subtracting a negative winds up as addition. Now notice this formula also works perfectly well, because if I try a point, say, negative x equals negative 4, well, what's the distance from negative 3 to negative 4? Well, if we plug in negative 4 plus 3, we'll get the absolute value of negative 1, which is 1. And it is a distance of 1. That makes sense. But what happens if we put in positive 4? Well, then we get the absolute value of 4 plus 3, which is 7. Well, what's going on there? Think about the number line. Here is negative 3. Here's 0. Here is positive 4. Well, what's the distance between them? Well, from 4 down to 0 is 4. From 0 down to negative 3 is another 3. So there is, in fact, a distance of 7 between positive 4 and negative 3. And that's what the formula gives us. So the formula actually works. If you're having trouble making sense of why the formula works, try plugging in numbers and thinking about where they are in the number line, and that will help you understand. So now, let's think about one more example of this. The distance of x from positive 2, again, we subtract x minus 2, absolute value of x minus 2. But the distance of x from negative 2, we're going to subtract a negative 2, and the subtraction winds up with it looking like addition. And so again, this is anti-intuitive. People see the switch in sign. How come the positive and negative goes to a negative and positive? Sometimes it really confuses people. What's going on is we're performing subtraction. When you subtract a positive, you get x minus 2. When you subtract a negative, you get x plus 2. And again, plugging in numbers and thinking about numbers on the number line can be a good way to think about this. Here's an equation. Pause the video and see if you can solve for this equation. Find the values of x in this equation. Okay, so what we're saying is, whatever x is, it is a distance of 4 from the location 1 on the number line. And so we could just find 1 on the number line and then walk a distance of 4 in either direction. And so if we walk to the right, we get to x equals 5. If we walk to the left, we get to x equals negative 3. So those are the solutions. The solutions are x equals negative 3 or x equals 5. Here's a practice problem. Pause the video, think about this, and then we'll talk about this. Okay, Now, this is a question where you might be tempted to do a lot of calculations, and you don't actually have to do a lot of calculations. Let's think about this. We have 37 here. And the two solutions to this equation are a distance of 25 from 37. So we're going to go up to here. This is some distance of 25. We don't even care about that location. The other is a distance of 25 down here. We don't care about that location. All we know is that this is x1 and this is x2. Well, what's the d is the distance between x1 and x2. Well, that is just 25 plus 25, which is 50. And so d equals 50. In summary, when we multiply or divide like signs, the result is positive. When we multiply or divide unlike signs, the result is negative. Absolute value is the distance from 0. Order of operations. Some folks might remember this topic as PEMDAS. In this video, we're going to expand the view a little. The first idea we need to discuss is the idea of a mathematical grouping symbol. Any grouping symbol shows that certain operations are grouped together. What are the mathematical grouping symbols? Well, by far, the most famous is parentheses. And of course, anything inside parentheses has to happen before the stuff outside parentheses. Parentheses group those operations together. So that's one grouping symbol, but it's not the only one. Another very common one are square brackets or straight brackets. These have the same meaning as parentheses. There's really no difference. It's much more a stylistic difference. Some people prefer the square brackets instead of parentheses. What I prefer, if I'm layering several layers of parentheses, I like to use brackets as one of the outer layers. That's just kind of a stylistic thing. For example, something along these lines. In other words, if I had parentheses instead of brackets, it would be exactly the same meaning. Another one is the square root sign. So this one is tricky because it has two meanings. It has the meaning of take the square root, but it also has the meaning of group things together. If I have a bunch of things underneath the square root sign, those things are grouped together. They have to happen first before I take the square root and then before I do any of the operations outside of the square root. No operations can pass through the square root. That's very important. The square root symbol is a grouping symbol. Another one is the long fraction bar. So for example, if I have x plus 6 over x minus 4, that denominator, x minus 4, that's grouped together. That comes as a single unit. I can't, for example, cancel the two x's there because anything that happens to that denominator has to happen to the whole thing. They are grouped together. So this is another example of a grouping symbol. Another one, and this one doesn't really even have an official name. I'm calling it the exponent slot for lack of a better term. And what I mean by that is all the stuff that would be up in the exponent. So the x minus 7 here, that's up in the exponent. We have 3 to the power of x minus 7. That x minus 7 has to happen together. We have to do that first, then we can compute the power, and then we can do any operations that are outside of the exponent situation. So the exponent slot is also a grouping symbol. Notice the two meanings of each of these. The long fraction bar means both group and divide. It has those two meanings. The exponent slot means both group and to the power of. It has those two meanings. And of course, all this is perfectly clear when we have things written in proper mathematical formatting. Everything's clear in proper mathematical formatting, but translating to plain text is tricky. Well, what do I mean by this? Well, when you write an email or when you post something to a forum, of course, you're writing in plain text. When you're writing in plain text, you don't have full mathematical formatting available. And so this can lead to some problems. Well, here's what I mean. Suppose we have some expressions like this, and suppose we have to type these in email or in a forum. We have to type them in plain text. Let's say this first one, for example. Many people will make the mistake of writing it like this. And this is 100% wrong. Now, why is this wrong? So people look at this, they see 2 to the n plus 3, and they say, well, that's 2 to the power of n plus 3. Well, I'm just going to stick in the caret, and of course the caret does mean 2 to the power of, but the problem is, what exactly does this red expression mean? Does it mean that we're doing 2 to the power of the whole thing, n plus 3, or is this merely 2 to the n? We're going to calculate that power, and then separately at the end we're going to add 3. What's actually being grouped together? And the problem here is, as we just said on the last page, the exponent slot has 2 meanings. It has the meaning of 2 to the power of, but it also has meaning as a grouping symbol. The caret carries the meaning of 2 to the power of, but the caret is not a grouping symbol. And therefore we need to substitute in our own grouping symbol to encapsulate the grouping symbol meaning that was written on the left side of the equation. So the correct way to translate this into plain text is like this. We have to supply our own grouping symbol to show how things are grouped. Similarly, we have an expression with a long fraction bar. Many people will make the mistake of writing this like this. And of course, this is an unholy disaster. This is completely wrong because, again, we don't know what's in the denominator. We have 1 divided by, and then is it just y? Is it y minus 7? Is it y minus 7 plus 3? We have no idea from the way it's written right there. Once again, the long fraction bar has 2 meanings. It has the meaning divided by, and it also has the meaning of a grouping symbol. The little slash, the inline slash, that carries the meaning of divided by, but that's no longer a grouping symbol. So we need to supply our own grouping symbol once again. So here it is written correctly. So in some ways, this might strike you as an inconvenience. It's sort of an accident of our current technological state that all these things, we're sending lots of messages in plain text. In plain text, we can't do the mathematical formatting. I actually look at it as highly advantageous because when you have to translate mathematically formatted information into plain text, it forces you to think explicitly about the nature of the grouping symbols. And if you're thinking explicitly about the nature of the grouping symbols, you're thinking much more deeply mathematically. So I would say even if you don't have to send any emails, even if you don't have to send in any support tickets to Magoosh, even if you don't post in the forums, at least practice translating mathematical format information into plain text. Practice this and make sure you understand the grouping symbols because that's something very important mathematically. Okay, now we can talk about order of operations. Many people call this PEMDAS, but I will call it GEMDAS. Now why am I calling it this? Because that first rank, that first priority, that's not just parentheses, that's all grouping symbols. All grouping symbols have the same level of priority in their grouping, in the grouping function. So the grouping symbols come first, then exponents, then multiplication and division, then addition and subtraction. Multiplication and division are at the same level, addition and subtraction are at the same level. So these are the 4 priority levels of GEMDAS. For example, let's solve this. So of course we have to do what's in the parentheses first. 7 minus 5, we get 2. Then we have to do the exponent. So now we just have a single number to a single exponent. So we'll do the exponent. 2 to the 2 is 4. Then the multiplication. Then the addition. Another example. Here we have something that presumably was grouped under a long fraction bar, and it's written correctly. So first we have to do what's in the parentheses. 10 minus 7 is 3. Then I'm going to do some multiplication and division at the same time. I'm going to multiply the 2 by 3. I'm also going to divide the 12 by 3. The final multiplication is the 9 times 4, and then add 6, and that's the answer. I want to re-emphasize a point in the previous problem. Multiplication and division are at the same level of GEMDAS priority. So we have some choice about the order in which to do them. For example, suppose we have A times B divided by C times D. So written like this, it's suggesting that we multiply the product A times B, we multiply the product C times D, and then we divide those two products. So we could do it in that order. But we could also do it like this. We could take B, we could divide by C times D, and then once we're done, we could multiply that whole ratio by A. Or we could do this. We could do A divided by D. Separately, we could do B divided by C, and then just multiply those two quotients. Or we could do this. We could do A divided by C, multiply by B, and then divide by D. So I hope by showing these different orders, I'm giving you a sense of the different ways that you can rearrange things. As long as you're always multiplying by the same things and dividing by the same things, as long as those two don't get swapped, you can swap around the order in any way that you want. And given that you can change the order in any way you want, is there any particular goal you should have? Well, yes. Always choose to cancel before you multiply. And this is something we're going to talk about in considerable depth when we talk about fractions in the upcoming videos. Finally, if there are multiple layers of parentheses or grouping symbols, we have to work our way from the inside out. So in other words, we take the innermost grouping symbols, and then at that innermost level we do exponents, then multiplication and division, then addition and subtraction. Then we move outside to the next layer, and we keep on moving out and repeating all the PEMDAS priorities, all of them at each level of grouping. So for example, here I have a long fraction bar, so we have to handle everything under the long fraction bar before we do anything else. Within the long fraction bar, we have parentheses, so that's another grouping symbol. So first thing I have to do is those innermost parentheses, 13 minus 11. So that becomes 2. Now, still under the long fraction bar, I have to do all that. I have to do 2 to the exponent, then I have to do the multiplication, then I have to do the addition. Now we're down to a single number. So now we can actually divide. We can divide 60 by 20, of course that's 3, and then add 2 and we get 5. So that's how we have to handle multiple layers of parentheses and grouping symbols. In summary, the very first thing we talked about is the very important idea of mathematical grouping symbols. Then we talked about translating grouping symbols into plain text. And again, this is not a trivial operation. If you can do this correctly, if you can do that translation correctly, you understand some deep mathematical ideas. Then we talked about order of operations, which I call PEMDAS, grouping symbols, exponents, multiplication, division, addition, and subtraction. We emphasize that multiplying and dividing are at the same level of priority. That gives us considerable choice about how we will rearrange what order we'll do the product and the quotients. And finally, with nested grouping symbols, we have to work from the inside out.